Welcome and thanks for watching this video dealing with components of vectors. Specifically, this video is aimed at my grade 11 U physics students as part of the Ontario, Canada curriculum in physics. This video is the first of two videos that will explain the concept of components of vectors. The video was made to complement in-class work and give the students an opportunity to practice and comprehend the skill of finding components of vectors. Specifically, the video will be what components are, what they mean from a physics point of view, how to work with them mathematically, which will be demonstrated in video number 2. So this first video deals with the basic concept of what components are, and the second video in this series deals more with the mathematics of components. So let's begin. First of all, let's review what exactly a vector is. Do you recall from earlier concepts in physics what a vector represents, what parts there are to a vector, what each part represents, what they are called? You may recall that a vector is simply any directed line segment, or in geometry terms, it would be represented by a ray, a line segment with an arrow indicating direction. In physics, the length of a vector represents or is proportional to the magnitude or the size of that physical quantity that's being represented by the vector in the first place. And you can see some examples here. This is a velocity vector, an acceleration vector, and here is a vector that represents position. The length of the vector, remember, represents the magnitude or the value of that particular quantity. So if this was the acceleration due to gravity, it may represent 9.8 meters per second per second. On the other hand, the arrow represents the direction in which that quantity is being directed or moving. With regards to direction, I am going to use the convention of direction based upon the compass cardinal directions, that is north, east, south, and west. The term component, as it is being used here, and as I will refer to it, simply means a part of, or is made up from, or contributes to a greater whole. So let us begin by looking at the vector that would represent a particular force vector, for example, an applied force that might be acting on some object. So we'll take a force vector here and put this on the Cartesian grid. And in this case, we're going to place a vector on a two-dimensional plane so that we can see that the head of the arrow ends at a unique coordinate point. As such, the length of a vector or its magnitude is defined or set by the two endpoints. In this case, I've chosen the vector tail to begin at 0, 0. So here's the tail at 0, 0, and here is a unique point on the Cartesian plane. And that would be defined by 5, 0. 5 over in the x or horizontal direction, 0 units up in the vertical or the y direction. You can see quite clearly, I believe, that all of the vector's length or its magnitude comes from the 5, or the 5 units of length. This is the only quantity that contributes to the magnitude of this applied force vector. In other words, there are 5 units of force in this particular direction, and there are no units of force in the vertical direction. When the orientation or the direction of a vector is changed, for example, this vector here, the effect is to change the endpoint value of the vector. And again, this vector is uniquely defined by a new point, in this case, 0, 5. That is, there is no contribution at all in the x or horizontal direction, is indicated by the 0. And all of the magnitude of the force vector is given in the vertical or the y direction, 5 units of force. In the first situation, if I have some object that I'm applying a force to, in this situation, all of the force is directed to the right or to the east if we're using the cardinal directions. And there is no force in this direction. So there are 5 units of force to the right, horizontally or along the x direction. In the second case, it's the opposite. All of the force is directed to the north or a positive direction, vertically in the y direction. So there's two situations here that are perpendicular to each other. All the force is being directed to the right, and here, or to the east, all of the force is being directed to the north. So now ask yourself, what do you think would be the effect on this object if we applied the force vector in this direction to the east and a push of the force vector to the north? If we applied those two forces simultaneously on this object, what do you think would be the behavior? What do you think would be the effect on this object? Where would it go? Perhaps you said that the object in question here might go partly to the east and partly to the north, that the ultimate direction of this block might be somewhere in this quadrant here. Well, let's see if that is in fact the case. What might happen if we change the orientation or the direction of the vector? What might happen if the vector has an endpoint that is changed? The effect of this is to introduce another coordinate into the case, or into the situation, in this case, the vertical coordinate. So if I introduce this new vector, this vector has some aspect of direction to the east, and it has some aspect of direction to the north. It is really a combination of those two directions, or those two pushes. So if you said that the object might travel somewhere in this direction, you can give yourself a pat on the back because you would be correct. So we are now in a position of defining this new vector, this new applied force vector, in terms of two other forces, a force to the east and a force to the north that occur simultaneously. If I was to push this block to the east while at the same time pushing it upward to the north, it would take this trajectory or this path somewhere in the northeast quadrant. What do you think would affect the angle that this box takes? Do you think that maybe the size or the magnitude of the forces might have some effect? So we can now define this new vector as being a composition of two mutually perpendicular line segments, one horizontal or east in the x direction, and one vertical or north according to our compass directions in this y direction. Here then might be the contribution in the northerly direction, and this would be the contribution in the easterly direction. If this object was to be pushed easterly and to be pushed northerly at the same time, you might see that it would take a path something like this. We say that these two vectors are the components of this applied force vector. In other words, they are a part of this vector. They are a part of the triangle. These two sides help to define the hypotenuse of the triangle. And in fact, these two sides, the magnitude of these two sides, also defines the interior angle theta of this particular triangle. You might imagine that varying the lengths of these two sides, the magnitudes of these two sides, would have an effect on the hypotenuse of the triangle, and therefore also have an effect on the angle. So if I was to change the contribution of the force in the northerly direction, that would have a direct impact on my applied force vector. It would change not only its direction, it would also change its magnitude. Similarly, if I was to change instead the contribution of the component in the easterly direction while maintaining, remember, you can take vectors and translate them as long as you don't change the magnitude or the direction. It's the same vector no matter where I place it. Then I will have to then change my applied force vector in such a way that now it has a different magnitude and it has a different direction relative to the east. So take a moment to compare these two situations. This vector, oops, this vector, which represents an applied force of 5 units, or 5 newtons perhaps, to the east, and this vector, which also represents an applied force. How are these two vectors different? How are they the same? They are the same in that they both represent a force vector, an applied force vector on some object, and that force, the applied force, has a magnitude and it has a very definite direction. They are different in that, in this scenario, the force is directed only in one direction, whereas in this scenario, there are actually two forces at play. They are mutually perpendicular to each other at right angles, and it is these two parts or components that ultimately define or contribute this particular force. And by playing around with these two magnitudes, you then have a direct effect on the applied force vector. If you'll recall your basic grade 10 trigonometry, the right angle triangle specifically, we have some predefined trigonometric ratios, sine, cosine, and tangent, that we can now talk about a little bit here in terms of the sides of the triangle. In triangle math, this side that is opposite the right angle is referred to as the hypotenuse. This side, which is directly opposite our angle theta, is called the opposite. And this side of the triangle is referred to as the adjacent, which means beside, because it is the third side, the only side left, and it lies beside this angle. You might be thinking then that there are many, many possibilities of vectors in a two-dimensional plane. Here's a vector, for example. Here's a vector that has very, very little component in the east direction, and almost all of its component is northerly. And in fact, if we take it to the extreme, in this case, if we looked at before, all of the force component is to the north. In this case, all of the force component is to the east. And then we have everything in between. And not only can we just change angles, we can also change magnitudes. The applied force might be very, very small, or it may be very, very large. In every case, it is the two components of the vector that help to define both the magnitude of the applied force vector and its angle or direction relative to a predefined line, for example, the east. We might say this vector is east 12 degrees to the north, or we might say this vector is 12 degrees north of our predefined direction to the east. You'll recall we used that same terminology and those same conventions back at the beginning of the course when we looked at kinematics, specifically displacement and position vectors. The terminology, or the way we talk about this, is we say this applied force vector can be resolved or made up into its two mutually perpendicular components. The component in the y direction, or north, and the component in the x direction, or to the east. It's these two components that make this particular vector, and we call this resolving a vector into its two components. So then imagine now that this vector, if we were to apply a force on this object only in the easterly direction, you would expect the object to move only in the easterly direction. Similarly, if I was to apply a force on this object only to the north, then I would expect that my object would move only to the north. If, however, you have an object, perhaps you have one nearby, and you use one hand to push the object up on your desk, to the front of your desk, or to the end of your desk, and you push with the other hand to the right of your desk, then you will see that this object will move somewhere in this vicinity, in this part of the quadrant. What do you think will determine the direction of the object that you push on your desk? What might come into play and cause the object to move in this direction versus in this direction? What would happen if the angle was 45 degrees exactly from the east? Well, if you said it matters how hard I push on the object in either direction, that will affect its ultimate path. Give yourself another pat on the back, because that's exactly right. If you push harder to the east, then the object will go more toward the east. If you push harder to the north with a greater force magnitude, then the object will move more to the north. If you said, I must push equally in the north and the east for the object to assume a 45-degree trajectory from the east, then you would be right. It really is the relative magnitudes of the two force vectors that have a direct impact on where this object will go. If I decrease the value or the magnitude of the force in the northerly direction and really increase the direction or the magnitude of the force in the easterly direction, you'll see that I have to, in order to complete my triangle, I must adjust my applied force vector. And you could also think about it this way. Your applied force vector, wherever it happens to be on this grid, the applied force vector also determines or has an effect on the components that make up that vector. So, for example, you might be thinking, if I know one of my components, say 10 newtons to the east, and I know this angle, theta, and perhaps I can figure out or determine what is the magnitude of the applied force. Of course, two force vectors can have exactly the same magnitude as given by the length of vector, but be directed in different directions, and as a result, these vectors would be classified as being not equal to one another, although their magnitudes would be equal. But because they have different directions, they are not the same vector quantity. If we go back to our pushing of the object, and I mentioned to you about using one hand to push to the east and one hand to push to the north, then this will take a certain path. Of course, when you do that, when you normally push an object anywhere, you don't consciously think of the contribution of one hand and the contribution of the other hand. But that, in fact, is what is happening. And that is the whole idea about resolving or breaking up a vector, such as this vector, into its two mutually perpendicular components. So that ends the conceptual theory part about exactly what a component is and some of the terminology that you need to know. For example, we talked about resolving a vector into its two components. We mentioned that the two components were just parts of a triangle. We introduced the terms hypotenuse, or reintroduced the terms hypotenuse, opposite, adjacent. And we talked a little bit about trigonometry very briefly. As you can imagine, there's got to be math somewhere, and you would be most correct. So to view the mathematics of components, please watch the next video that is called Components of Force Vectors Math. Thank you very much for watching. I do hope that this has been some help to you. I realize that if you are not from my classes or my school, that some of the terminology, conventions, and vocabulary may not be exactly what you use, but the basics of vectors should be the same.